Did all of you receive all the files? I sent it to you, the lectures, the review. I sent it to you, the midterm one sample, last year midterm. Did you receive it, guys?
Yeah.
So please open it. Make sure that you open and follow me. We're going to start with review one, which is before lecture 8 and 9 in your lectures. So let me know about the lighting, and actually, no, today we're going to talk about review 1 and lecture 7. Whatever we have in lecture 7, we're going to continue. Okay, guys, can you see that? Can you see that, guys?
Yeah, it's clear.
Great, great. So hopefully today internet is much better and we are in school. So what's today gonna happen? We're gonna take the review, which is from before lecture 1. So review 1, we talk about thermodynamics, ENGR. We're gonna go through the definitions 130 of this course. This is review 1 of this course. We're gonna talk from chapter 1 until chapter 5, section 5.2. So what thermodynamics is? Thermodynamics is two pieces, thermo and dynamics. Thermo means heat, temperature, energy. This is usually referred to energy. This means change in the system. Something happened in our system, it changed it from one state to another. So we started with this brief introduction. Thermodynamics is the science of energy and entropy. You will see these words again in the exam. So for example, ask it, what is the science of, the thermodynamic science of complete, what and what? So you need to write energy and entropy, that's it. The same as quiz 1. Then we have brief introduction about first law of thermodynamics, second law of thermodynamics, even macroscopic and macroscopic. The first law of thermodynamics, if you remember, it was energy cannot be neither created nor destroyed, but it can transform from one form to another, from potential energy to kinetic energy to thermal energy, whatever, energy from one form to another. Second law, that you have always losses. That's what we're going to see this Friday. We're going to talk a lot about second law of thermodynamics from chapter 6 and define entropy from chapter 7 and go in details. We define something called macroscopic with I and macroscopic with A. Macro with I mean individual, if you remember, individual. Everyone by himself, what is going on. Macroscopic with A is a global, when we measure everything as one piece, as one system. We focus on this. This one, for example, is molecular dynamics. So when you talk about every molecule, every element, how it behaves, that's called macroscopic. But macroscopic with A, we are talking about global system. I'm talking about the fan. I don't care about anything except the overall of the fan. That's it. I care about the fan itself. So there is nothing else I care about. So everything here is my system. I see it as black box, macroscopic. However, maybe here something else, here something else, here something else, like pressure distribution, flow distribution. I don't care. This is microscopic. Thermodynamics is a sign of macroscopic. Many of the science that you talk about, like fluid mechanics, this is macroscopic. Like we see everything overall, globally, what happened. We talk about individually, about every molecule, every element of the system. This section 1.1, we have it in your notes, like introduction. Section 1.2, we talk about units and dimensions. In our life, we have 4 basic. Section 1.2, we talk about dimensions and units. This is very important. The unit gives a real value to a value. Without giving a unit, you do not give anything. Nothing has meaning, no value. The value behind the units. We have 4 basic dimensions: length, mass, time, and temperature. Length, L, mass, we use M, time, T small, temperature either theta or sometimes T. Both are correct. So T small for time. The units, we have 2 schools of units. We have 2 schools of unit. SI units, most important for us, bridge units. SI units, like for example, the length in meter, mass in kilogram, time in second, temperature in Kelvin. This is absolute temperature. Do not ever use anything else except those. Meter, kilogram, second, Kelvin. If you have temperature in Celsius, you need to transform it to Kelvin. So always here in Kelvin. Second, kilogram, meter. If you smart enough to use some kind of simplification, it's okay, it's up to you. But if you always use these 4, you will never ever get lost, ever. There are tons of things coming out of those. For example, area, momentum, force, energy, power, pressure, everything of those coming from area is meter square, for example, this is square. Momentum, mass times velocity, meter, kilogram per second. Force, rate of momentum, which is kilogram, meter per second square. Or force equal mass times acceleration. Energy, force times distance, so kilogram, meter square per second square. But power is rate of energy, which is kilogram, meter square per second cube. Pressure, which is force per unit area, force per unit area. We're going to discuss in details about pressure. So pressure is kilogram per meter second square. We said, for example, this force we used to use Newton. This energy we used to use Joule. This power we used to use Watt. This pressure we used to use Pascal. Similarly, for the bridge units we're using for these 4 feet, slug, second, and Rankine. Do not use anything except this 4. For example, Rankine. If you have temperature in Fahrenheit, use Rankine. Do not use anything else. The same for the force, energy, need to come through these 4 independent or general dimension scale. We talk about system 1.3. Okay, guys, I'm gonna go fast, but I'm gonna redefine everything we took during the course. So in Module 3, we define system. What a system is? System is a matter of space that we are interested in. Region of space we're interested in. 1.3, system. And boundary, surrounding. We're gonna go solve an exam with together. System is region, for example, region of space that needed to be studied. You can use any other words if I so ask you to define system. Boundary is the limit or outer line of a system. Separate the system from the surrounding. Everything else surrounding the system. For example, the fan. I will plot like here, the fan. If this is a fan, this is the system. The green line is the boundary. Outside is the surrounding. This is surrounding. This is the boundary, the limit. This is the system here, side here, anything here. Overall, that's global, macroscopic. I'm looking for the whole system. The whole thing is one piece. Here, I give power. I took power. I give mass. I took mass. This is called a system. I see it as one piece, one block, black box. I don't care about details. I care about what happened across this boundary. System has 2 types. two types: open system and closed system. Open system, we have control volume, like this problem. Closed system, we have control mass, like tank, rigid tank, and piston cylinder. Open system is very commonly famous, like the last section we talk about, 5.2. This is open system. Diffuser, nozzle, turbine, fan, compressor, anything almost surrounding us is open system. There is mass can cross the boundary. Mass can cross the boundary. Here, no mass can cross the boundary. Like rigid tank and piston cylinder. Okay, which call it control mass. Rigid tank, there is no mass or even a change in the volume. So you use constant specific volume. We talk about property. Property is a characteristic in the system, like pressure, density. So we have two types of properties. Property itself, 1.4, is a characteristic of a system. Characteristic mean something describe the system. Characteristics is characteristic of a system. Some characteristic like pressure. We have two types of properties: intensive versus extensive. Depends on the size. Something intensive. Intensive property. So intensive property, like I said, I is independent of the size. It does not depend on the size of the system. Independent is in here. Independent of the size of the system. For example, extensive property, like for example, mass, volume, energy, internal energy, potential energy, kinetic energy. We have, for example, number of moles. In other side, we have commonly pressure, temperature, density. We said, if you want to change any extensive property to be an intensive, you have a very beautiful trick, which is divided by mass. It goes from extensive property to be an intensive. For example, this will become volume. Volume over mass would be a specific volume. We use this V, which is 1 over rho, by the way. Volume over mass. How much volume do you have per unit mass? It's independent of the size. If you have a specific, if you have water, almost water, and 1 atmosphere, 20 Celsius ambient temperature, it's almost 0.001. Almost. No matter what you have, it's 0.0001, 0.001 meter cube per kilogram. It's almost 1 liter. 1 liter of water per kilogram. Almost. That's very good because it's depending on the size. If you have a very huge prototype system, like steam turbine, like even steam station, is still the equation valid. The result is the same because it's per kilogram. If you have small prototype, a small model, a small design, the same results can be the same specific in anything specific, the same between two systems, small and big. But here, no, it depends on the size. This depends on the size, extensive properties. So the watt here, the energy I talk, is different from the energy here. I mean, between two systems. So this is depend on the size. How big your system is, how small. How much mass do you have? How much volume? Like for example, specific energy, specific internal energy, specific kinetic energy, specific potential energy, specific number of mole, specific number of mole. So everything is specific. Actually, we have two special cases. It's divided by mass, number of mole by the mass. We have two special specifics, which is specific gravity. Specific gravity is something not that important. Specific gravity is rho over rho water at room temperature. This is something just trivial, just giving the density in other way, specific gravity. And a specific heat capacity like Cp and Cv. Yeah, it's per unit volume, but also per unit temperature. Shows joule per kilogram Kelvin. It's per unit mass, sorry, and also Kelvin temperature. So specific heats and specific gravity They are a little bit different from specific properties, like specific volume, specific internal energy, specific kinetic energy, potential energy, specific number of mole. So anything specific, usually we divide by mass, except these two special cases. A specific gravity, just any row. For example, a specific gravity of mercury, Hg, I think 13.6. It means that the density of mercury is density of water, 1000 times 13.6 is 13,600 kilogram per meter cube. This is the density of mercury. Specific gravity of copper is like 8.9. Specific gravity of steel, 7.8. It's a ratio between density of the material over density of water. Specific gravity of, for example, wood, 0.7. It's lower than the wood, that's why it floats. The specific gravity of material is the density of material over the density of water. If it's lower than 1, it floats. Greater, it dives in the water. Okay, guys? Any questions? Any questions? I'm fast because we already have heard this before. Guys, are you here?
Yeah.
Yeah.
So I'm kind of fast because we already discussed this before many times. When we go to state postulate, we said that we need two independent intensive properties to get the rest of the properties, independent of the size of the system. 1.5, it's density and specific volume. Just 1.5, as you know, nu equal 1 over rho. That's it. And 1.6, we discuss the state. The state. I'm not going to use number. I'm going to give the definition. State. We have process. We have process, and we have state process. We have cycle. State. What was it? What we said. What? How about states? I did not mention here. Oh, okay. A state is. Let me remember. Yeah, we have. No, maybe before that, we have equilibrium. Equilibrium mean imbalance. Imbalance in temperature. Thermal equilibrium. Every thermodynamic problem is thermal equilibrium. Temperature is the same throughout the system. Throughout the system. Temperature does not change. That's why we define later the zeroth law of thermodynamics. Temperature is the same. If you have water and copper, both copper, they are in similar equilibrium, it means temperature here is 50, temperature for this ball is 50. They are in thermal equilibrium. Temperature is a measurement of hotness or coldness. It's not energy directly. It's not measurement of energy directly. It can measure energy flow, but it's not exactly the same. It's a measurement. It's a measure of hotness or coldness of a system, and we define it in lecture. So this is 50, this is 50. This is called thermal equilibrium. They are the same temperature throughout the system. State is set of properties. Together, we call it a state. For example, if you have a state here, some fluid in piston cylinder problem, and it has pressure, temperature, volume, a specific volume, mass, whatever. This is called state. If you compress it, another set of property, it's called another state. This is 2. Between 1 and 2, we call it process. We call it a process. If you go 1, 2, 3, 4, 5, and you go back to 1, we call it cycle. Cycle is set of processes that returns back to initial state. It must be returned back to initial state. You can rephrase it as you wish. So you start at 1, I think you can see. You start at 1, go 2, go 3, go 4, go back to 1. This is very famous steps like this. Any two properties, B and A. Any two properties, you go from 1 to 2, 2 to 3, This is process 1, process 2, process 3, process 4. Lots of process. But you go back to 1, this is called a cycle. We like this cycle to analyze our system. For example, the area in this shape is how much work you gain. The area in this is this PV diagram. The area between these 4 sides is how much energy you gain from this system. You paid some fluid and you get this energy, the whole area. The process itself, if you, for example, plot PV, this is the work between just one A and B. This is this 1 to 2, state 1 to state 2. This area is the work, yes, correct. Or work per unit mass. But here, for the whole system, called the cycle, whole cycle. So everyone is the area. If you 1 plus, 1 minus, 1 minus, the overall is the area inside the curve. We're going to discuss that later in chapter 6. Instead, guys, we have some special cases in processes. Some processes has constant property. For example, if the temperature is constant, we call it isothermal. So we have 3 special cases: isothermal, we have isobaric, we have isochoric, or isometric. We have other things like isentropic, like constant entropy. We're going to define it later. For isothermal, temperature is constant. The temperature does not change in the system. Isobaric, pressure is constant. P1 equal P2. If it's 1 to 2, if it's 2 to 3, P2 equal P3. Isochoric, like rigid tank. Isometric, volume is constant. V1 equal V2. Isentropic, the entropy is the same. We're going to define this later. Okay. Okay, guys, any questions so far? We're going to use this kind of notation to simplify some equation like work. We're going to see that. Energies, section 2.2. 2.2 and 2.3. Energy. We have 3 sets of energy and we have total.
That's right. It's really blurry.
Oh, now?
Oh, now it's good. Yeah, there we go.
Okay.
You just focused.
Okay. Need to focus, guys. No, just a joke. So energy. Actually, I uploaded yesterday the videos. Did you not see the videos, guys? Did you get the videos? All the videos are uploaded for you. Yeah, I post all the lectures. This Friday, Friday is the exam, 17th. All the lectures are online. No, you will not have quiz today. This Wednesday and maybe next week we have all the quizzes. Like this Wednesday, next week, Monday, Wednesday, and Friday we will have quizzes. The 5th week of our course will be totally quizzes, and every quiz will be in the previous lecture. I will post for you also, as we agreed. We will having 15 minutes, 5 for the questions and 10 for the uploading, please. And for midterm, it's 1 hour midterm and 30 minutes to upload the midterm. However, I recommend to upload as soon as possible. And do not cheat. If you cheat the steps even from somebody else and they are wrong, not even the results, you get 0. Do not cheat from anyone. You will regret. Do it yourself. It's easy. There is nothing easy and hard. There's something you know or you don't know. Okay, guys? Energies. We said we have internal energy. We gave it simple U. I mean letter U, uppercase. Total internal energy. We have kinetic energy. Like key E. Extensive property. We have potential energy. Give it PE. Because internal energy, the total of all the internal energy, like nuclear energy, molecular energy, nuclear and molecular. It's half mv square. This is kinetic energy. V is velocity. This is mgz, and g is altitude, elevation, your height. How much different the potential energy. And we say the total energy is E, is total energy. of a system or flow is called U plus PE plus KE, total energy. If there is no change in a system, this energy is supposed to be constant. If you don't have any other changes. For example, this bin, it has kinetic energy, potential energy from here to here. If I drop down, the kinetic energy will increase, but potential energy decreases until when it touches the ground, the potential energy is zero, but kinetic energy reach maximum. So the total energy is constant. PE plus KE equal constant. PE equal PE plus EE KE constant until it touches the ground. We divide by mass everyone, and we get specific. We divide by mass, we call it specific. We divide by mass, we call it specific kinetic energy. Have V squared. We divide by mass, we call it specific, PE small, GZ. We divide by mass, we call it E small. We call it, this is specific total energy, a specific potential energy, a specific kinetic energy, a specific internal energy. And for every one of those, we define something. Temperature and the measurement of hotness are called this. Guys, you follow me in the notes. So I'm now in the middle of page 1. Temperature is a measurement of hotness or coldness of a system. 0 is low. If you have two bodies in thermal equilibrium with a third body, they are thermal equilibrium with each other. A and B in thermal equilibrium with C. A in thermal equilibrium with C. B in thermal equilibrium with C. So it means A and B are in thermal equilibrium. Okay, guys? This is Virew's law of thermodynamics, section 2.3. Actually, it's 1.9, but we push it back to 2 was these energies. What is that? Yeah, it's here. Okay, guys? If you go back through the lectures, this is the end of lecture 2, I think, so that we are speeding up lectures. Temperature has two sets of units. We said we have SI and we have British. SI, need to know this very well, and British. We said here SI, Celsius and Kelvin. And here we have Fahrenheit and Rankine. Celsius said, I'm gonna measure the freeze of the water reference temperature to be 0. And its boiling is 100. And you measure everything for that. For example, our body temperature is 37 degrees. That's our body temperature according to this scale. Kelvin, which is absolute temperature, is a much better, the correct one, is temperature in Celsius, for example, plus 273.115. So, for example, our body is 373, it's 310, correct? Kelvin. This is our body. Okay, almost. This is our body temperature. The water freezes at 273 and boils at 373. The Fahrenheit is another set of units, British units. He said the water freezes at 32 and boils 212. The water freezes at 32 and boils at 212. And the transformation from Celsius to this guy, Fahrenheit, temperature Fahrenheit equal 9/5 temperature in Celsius plus 32. So if this is 0, this becomes 32. If this is 100, this becomes 212. For example, our body temperature is, I think, 97, 96 Fahrenheit. Here is 37 Celsius. Here is 95. So different units. Without units, you give no value. Rankine is a shift of this, which is absolute temperature in British, which is temperature in Fahrenheit plus 4, 5, I think 9.7 or 6.7. That's constant. I mean, constant shifting. That's why delta R here equal delta R there. Delta R here equal delta R here. But between this and this, not. We have 9/5 between Celsius and Fahrenheit. Pressure, force per unit area. The very last section in the first chapter, which is pressure, force per unit area. Pressure, force acting per unit area. And we have P equal F/A. For example, Newton over meter square or kilogram meter per second square is Pascal. And we define something called Pascal principle. Pascal principle, which is the pressure, the fluid, the compressed fluid, incompressible fluid, translate the pressure throughout, confined, of course, confined. It means totally confined compressible fluid. Translate pressure throughout the system. The pressure is constant, the same. For example, if you have this system, whatever pressure here, exactly same as here. So F over A here, 1 equal F over A here, 2. This is Pascal principle. Pressure is the same throughout confined fluid. Apply pressure, it transfer onto here. So you can apply a very small pressure here, a very small pressure over a small area, you get huge pressure here. It's the same pressure, but huge force. Small pressure here, very small pressure. But because small area, you got huge pressure here, huge. You can lift a car with just small, with your finger. This area is so small, you can lift a car. We have 3 basic measurements of pressure. We discussed them last time with the lecture 2, which is this is a space. We said if you measure from here, we call it P absolute. If you measure, for example, from here to ambient, which is atmospheric pressure, we call this from here, we call it P gauge. And we call downward is P vacuum, we don't care. So P gauge, always P absolute minus 1 atmosphere. So whatever I give as absolute, subtract P ambient, it became a gauge. Or vice versa. If you have P gauge, add to it P atmosphere, it became P absolute. We care about absolute pressure. We don't care about gauge in our equation. However, we measure P gauge. So if you have a tire, you measure P gauge. You measure that. You have a pressure difference from ambient. How much pressure exceed in the tire of the bicycle?
Professor, we can't see on the, you gotta rotate the camera.
Oh. Sorry. So we have 3 measurements. We have absolute pressure, gauge pressure, and we have vacuum pressure. We care about the absolute, which is from space, 0 pressure. We cannot have negative pressure. It's impossible. Negative pressure doesn't exist. 0 pressure means no fluid. You are in space. Whenever you have fluid pushing you, it's a pressure. 10 Pascal, 1,000 Pascal, 10,000 Pascal, until you get 1 atmosphere. It's almost 101,325 Pascal. This is 1 atmosphere. 1 atmosphere pressure, guys, it means in our shoulder, we carry fluid from here to the end of the atmospheric pressure by this weight over area. It's a force per area. This is how much mass we carry in our shoulder until the end of the atmospheric pressure, atmospheric domain. Okay, guys? So we have from here, from 0 pressure, from space, there is no absolute pressure. And negative 1 absolute from gauge. If you measure P absolute from here. If you measure P gauge from here, positive. So B gauge is P atmosphere plus B absolute plus P atmosphere. Actually minus. So B gauge is negative if this is 0, for example. It's negative 1 atmosphere. So if you have pressure atmosphere exactly, B gauge is 0. So if you P absolute is exactly P atmosphere, the B gauge is 0. You have no gauge pressure. The tire has no air. Or it has air, but it has no pressure difference between this inside and outside. When you pump it, the B gauge increases. It means your absolute pressure became greater than atmosphere. When you pump it and push air, compressed air inside the tire, the pressure build up. It became greater than 1 atmosphere. Then in chapter 3, we talk about phases. We talk about phase and phase change. So we talk about block of ice. If you remember, we took block of ice like negative 15. We heat it up, temperature increases until it became 0. This is 1 atmosphere, for example. And we heat it up, the temperature does not change. This is heat versus temperature. The volume almost the same, but the energy, the temperature is the same, which is 0 Celsius at 1 atmosphere. Remember A, B, C, and we call this fusion, latent heat of fusion. Some energy transferred from complete ice to complete liquid. Then we heat it up, it became liquid. Temperature now increases. Until certain temperature, which is 100 Celsius, there is no increase in temperature. It became some vapor shoot up. As long as you keep the temperature 1 atmosphere, and pure water, this became like this. Then a vapor starts to show up here, superheated or vapor. This is called evaporation. Latent heat of evaporation. Energy from here to here, we call it evaporation. This is fusion. Then we said, okay, let's talk about this one, and we call it steam table. This is a pressure curve in PV diagram. So let's plot TV diagram. This is the phase change table with steam table. We call it a steam table. A steam table. We have volume, temperature. We have volume, pressure. This is the two famous curves. Guys, you have any questions, guys? If you go, it said that B absolute equal B ambient, there is zero gauge pressure. It's called zero gauge pressure. So always B gauge is B absolute must be minus 1 atmosphere. That's it. B gauge equal P absolute minus 1 ampere pressure. So whatever you have absolute, subtract 1 ambient, became B gauge. Like measuring the pressure inside the tire. This is a very fundamental problem. When you pump your tire, if it has zero gauge pressure, no, it has pressure, absolute, which is 1 atmosphere, but has zero gauge pressure. So when you pump air, the pressure build up greater than atmosphere. Now we measure B gauge. So the TV diagram look like this. We have curve like this. We describe this in details. We have constant pressure lines. Along this line, guys, the pressure is constant, 1 atmosphere, half atmosphere, 2 atmospheres. The same for the PV diagram. Very similar curve, but the constant temperature line like this. Like 100 Celsius, 50 Celsius. So here, the constant temperature line horizontal. This is constant temperature line. From here to there. This is like if you have XY, I asked you to plot Y equal 9. You're gonna say this. This is Y equal 9, correct? This is X equal 5. So this point is called 5 and 9. Independent, two independent properties. Two independent properties. X equal 5, Y equal 9. You can get this point, correct? Yes. X equal 9, a line perpendicular to Y. Y equal 9. X equal 5, a line perpendicular to X. It's normal on X. It's called X equal 5. So this is X equal 0, X equal 1, X equal 2, X equal 3, X equal 4, X equal 5. This is called the Cartesian coordinate system or Cartesian coordinate system. So temperature constant is this horizontal line. Vertical line is constant specific volume, like rigid tank. Rigid tank, you only have vertical upward or downward. Rigid tank. If you are here, go there or go down. If you are heating up or cooling down, for example. So this is called constant specific volume. Isochoric, isometric. Constant temperature, isothermal. Constant pressure like this. It depends on the phase. So if you are compressed liquid, increases. Superheated region, the same here. This is the pressure. Constant pressure, horizontal. Constant volume, vertical. Constant temperature, like this. Because pressure and volume inverse proportional to each other. Decreasing the pressure increases the volume. That's why you see this. Because we don't care about temperature. Temperature is constant. We don't care about temperature. How the pressure volume behaves like this. Yeah, here, the constant temperature line, the constant pressure line, the constant volume line. We know names for them, isothermal, isobaric, isochoric, or isometric. Now, we have 3 regions. Compressed liquid, subcooled region. Mixture, saturated mixture. And we have superheated vapor. We have 3 regions, 2 lines, saturated liquid, pure liquid, X equals 0. We call it F. Any subscription is F, liquid. We have saturated vapor. Saturated vapor, X equal 1. Quality is 1. We use G. Mixture, for example, for water, we have table A4, A5, A6, A7. This is both of them mixture, saturated mixture here. HF and HG, VF and VG, UF and UG, or a difference in A4 and A5. A4 temperature input, A5 pressure input, A6 superheated region, A7 is compressed liquid. And this point we call it critical point. 3 regions, 2 lines, 1. 3 regions, 2 lines, 1 point. 3 regions, 2 lines, 1 point. I'll ask you in the exam, plot them for me. Give me constant temperature line here or there. I can ask you for this or this. Plot for me. Do this. Give me this line. Give me constant specific volume. You're gonna draw a line like this. V equal 1.67 at 1 atmosphere, for example. Here V is 0.001 specific volume, meter cubic kilogram. Okay, guys? And we gave tables for that. Okay, guys? Then I said if you can get a state, if you have 2 independent intensive properties, if you have 2 independent, if I state, any state, if you have 2 independent intensive properties, for example, T and V, you can get the rest of the properties. If you have these 2, you can get the rest. For example, temperature was 100 Celsius. The volume was 3 meter cube per kilogram. If you go to the chart, you will see 100 Celsius, table, for example, A4. This VG is exactly 0.001. This VF, actually this VF, this is VG is 1.69. It means you are superheated, you are here. So temperature, you are here. So your pressure is so small. You can go to table A7 to get A6 to get this superheated region point. From 2 information, you can get the rest. You can get the volume, the pressure, internal energy like U, H, entropy, anything from 2 independent intensive properties. The same if you have PV, if you have TMP. But TMP, you cannot use, for example, TMP here because they are dependent. I cannot give you temperature is 100 and pressure 101 kilopascal. You cannot get anything because this is a line, it's not a point. Temperature is 100 and pressure 101 because they are dependent. They are dependent on each other. So you cannot get the rest of the properties, but I need something else. And we define something called quality. It's mass of the vapor over total mass. Mass of the vapor over total mass. And we used to use V equal VF plus X VFG. U plus equal UF plus X UFG. The same for enthalpy. Enthalpy is H by definition, U plus PV. This is enthalpy. We have H equal HF plus XFG. So in the table you have H and HFG. That's the subtraction between HG minus HF. So you can get the enthalpy. If you want total enthalpy, it's MH small. And always remember, in the V equal V over M. The specific volume is volume over mass. Always remember this. Let's take a 5-minute break and come back. Okay, guys?
Yep.
Okay, take a 5-minute break, guys, and come back. If you have any question, answer, ask me now. But all of you can go leave and come back exactly at 11. Exactly.
Can I just see the board real quick, Professor? I'm still writing.
Yeah, sure. I'm sorry. No, I'm sorry. So, guys, if you want to take a break, please leave and come back at exactly 11. Okay. I'm gonna close now, but you can take rest from me. 7 minutes, 8 minutes break, then come back at 11. You have any question, guys? The people are here. Anyone has any concern? Any problem? I'm fast because you already knew this. You have heard this many times from me. I don't know how many times I said 2 independent intensive properties. I think it's many. 100 times maybe. Okay. You need to know how to use this table. You need to use it a lot. You did it already in homework 1, homework 2, and homework 3, homework 4, homework 5. You always use steam table. So you need to be good in using steam table. If you have two independent intensive properties, you need to find a way to find them. Sometimes the data explicitly not given. So you need to do something called interpolation. So if you have two information and you want to get some information in between, you need to do interpolation, which is the slope is the same or the similarity between two triangles. So this is based on the similarity of two triangles. Anyway, so let's see this way. Sometimes you have the data like, for example, 320 and you have 280, like 280 and 320. And you want here the 300. So you do what? Average, correct? Correct?
Yes.
If you have, for example, 290, what you do, guys? You may do interpolation, or you notice that this is from here to here is 1/4. So the value here take 3/4. It's closer to this. This from here, it's 3/4. It takes 1/4. It means if you have VF here and VF here, and you want VF here, it's 3/4 this value plus 1/4 this value. If you are, like for example, average, it's 1/5 here, 50/50, plus 1/5 of this, 50%. If you exactly here, it's 1 from here, 0 from here. The closer to this, the bigger the ratio is, like cantilever. The same for this guy. The bigger the distance, the small. So here, from here to here, it's 1/4 the whole distance. 280, 290, 300, 310. This is this 1/4, give it to this. This to here, 3/4, give it to that. It means if you want VF here, it's a 3/4 VF at 280 plus 1/4 VF at 320. And this is VF at 290. Correct? Make sense? Make sense? Does it make sense, guys? No
Yeah.
one? Does it make sense for anyone?
Yeah.
So if you want, I recommend interpolation. You need to find a technique that you have it and you scale it and you may fasten that. Some of you may write a code, a small code, input 4 values, give me the missing one. Like 5 values, sorry, give me the missing one. For example, give x1 and x2, y1 and y2. If I give x here, I give y. If I give y, I give x. Any 5 inputs, I get the 5th. Or 5 inputs, give the number 6. Okay? So you can write code, it's okay with me, no problem. You need to find that you are an engineer. You need to find a scaled way, fast way. But if you did them wrong, I'm gonna count the last value. But if you show me steps, I will give you more credit, even if it's wrong. So you need to make sure that you use this table more efficiently and more. We said we have either a steam table or equations. Like for example, ideal gas law. Ideal gas law, it's only for gases. Only for gases. I'm repeating that over and over. Only for gases, not water, liquid. Not, for example, any fluid, liquid. But gas phase, like for example, if you hear hydrogen, oxygen, nitrogen, air, argon, these are assuming are ideal gas or ideal gas, or maybe vapor, water vapor. It can assume it's ideal gas if I said that in the problem. But generally, this means ideal gas. Ideal gas, PV equal RT, or PV over RT equal 1. And we define something called compressibility correction. Sometimes this equation is wrong. For example, there is like steam vapor table A6. Compressibility correction, Z. Z equal PV over RT. So this is V ideal. This is V actual. If you have pressure and temperature, you can get actual V from Nelson chart, table 8-18. So you can, from here, you can get V actual. But this is V ideal. It's a very ideal. It means Z equal 1, which is not correct. Z is 0.98. 0.96, 0.8. And this is much closer to the reality. This is the reality. This is the real value, the measurements, the experimental results. This is approximation. So PV ideal over RT equal 1. PV actual over RT equals Z. This is from chart, Nelson chart. Nelson chart.
Professor,
Nelson chart. Yes, sir.
Could you refocus the camera, please? It's a little blurry.
Sure, sure. How about now?
It's still the same.
How about now? Is it good now? I see it good here. I don't know. Is it good or not?
It's kind of still the same.
I don't want to go back because going back it gonna be make it worse.
Can you just write bigger? Just keep it where it was at, and then
Yeah.
just write bigger. Yeah, I think that'll just be
How
better.
about still?
Yeah, it's still really bad.
How about now?
No.
No, this is the actual camera of the laptop. You do the focus from here. I think there is a bottom here. I hate this kind of simple things that make the lecture ruined.
That focused, but I don't know if it's the internet or not.
No, the internet is so good. This is a school internet and wired. It's not
it's good
even
now.
Wi-Fi.
It's good,
Good
now.
now.
It's actually really good now.
Okay, I wish that remained like that. Okay, so anyway, so we have this Nelson chart. You go with P reduced, T reduced to get the V actual. Here, you go with P and V, P in absolute and temperature in absolute in Kelvin, you get the V ideal. Okay, remember these kind of words. You're gonna see them in the exam, but a little bit different. So you need to be smart enough to figure out what's going on. So heat and work. Heat, we use the symbol Q. Work, we use W. Heat, Q, is energy added to the system in the source of thermal energy. Work.
Professor, it's not.
Yes.
It's not focused again.
Oh. How about
That's
now?
good. Yeah, that's good.
So heat addition to the system, work done by a system. So this is usually in, is usually out. Positive and positive. If the work is in, it's negative. If the heat is out, it's negative. So we do, this is positive and this is positive if it's out, if it's in to a system. So system here, imagine this, Q and W. This is positive and this is positive. Otherwise, this is negative. Otherwise, this is negative. Remember this quick chart. If I told you in a problem, this is adiabatic, it means Q is 0. There is no heat addition or rejection from this system. Frictionless. Frictionless meaning the same thing. There is no heat due to friction. Q also is 0. The work done by a system. W is integration P dV, or W small is integration of P dV. And we have 4 special cases. Constant volume, there is no work. Constant pressure, P dV. Constant temperature, You can use ideal gas law to make it simplified. If it's gas, it's always area under the PV curve. This is area under the curve. If you have PV curve and you go from state 1 to state 2, this is the work done or work given. If it's positive or it's negative, this is called PDV. We have 4 special cases and polytropic. If it's power n, P equal or proportional to V to the n, or actually BV equal constant, like this. This is called polytropic equation. This is polytropic parameter. If n equals 0, it's isobaric. If n equal 1, it's isothermal. If n equal infinity, it's isochoric. If n equal 1.4, it's called isentropic. If n equal k, specific heat ratio, we call it isentropic. But we're gonna say that later. But for now, you need to know PV to the n equals C, constant. It means P1 V1 to the n equal P2 V2 to the n. That's mean constant. This is the constant. You can substitute by P in terms of V and integrate. The whole idea to replace pressure in terms of volume to be able to integrate. This is work per unit mass. This is specific volume. The same for Q. If we divide by mass, it became heat per unit mass. Do not ever say a specific heat or specific work. Do not say that. These are not properties. That's why we use delta for them. They are inexact derivative. They are not property. They are not like W1 minus W2. It's not like that. But yeah, volume, yes. V1 minus V2. And P the same. Temperature the same. Internal energy, yes. Current energy, yes. Potential energy, yes. But W and heat, nope. They are not properties. They are associated with a process. They path dependent, depend on the path. How? Path. From where to where? Path. Yeah, I'm fixing the TH, path. So we have a lot of formulas, special cases in the end of page 2, how the work look like. For example, constant volume, constant pressure, constant temperature. For example, ideal gas. But constant pressure and constant volume, it doesn't matter. Only number 3, constant temperature for gases. Number 4 for gases also. The polytropic form. It's end of page 2 in your lecture. We first law of thermodynamics, chapter 4, Q minus W equals delta U. Heat addition minus work done equal change in internal energy. We have 2 special cases. Rigid tank and piston cylinder. Rigid tank, Q equals delta U, because there is no work. Volume is constant. Work is 0. Piston cylinder, constant pressure. It means Q equals delta H. You can use the same equation, but I can replace this by PDV, which means delta U plus PDV, it's delta H. Enthalpy is internal energy plus PV, which is Q equals delta H. This is rigid tank, constant volume. This is piston cylinder and constant pressure process. We talk about specific heats. For ideal gas, we have PV equal RT. Also, we have U equals CVT, or delta U, integration of CV delta T. Delta H, integration of CP delta T. The heat energy required per unit temperature per unit mass. It's called CV. Here's CP. And we go for 2 special or 3 special cases if we assume V is CV constant or we integrate it. We have R over R universal equal molecular weight. Or actually R universal over R. CP bar over CB equal molecular weight. The same for the rest. Molecular weight is constant for a fluid. For example, air, it's 29. It's table A1. Table A1. Some people use A, dumb M, or MW. Table A1. It has all molecular weights. Molecular weights is how much mass over number of moles. It's constant for a substance. How much mass? Kilogram per kilomole. Kilogram per kilomole. Then we give a last lecture. We talk about the continuity. Chapter 5. I'm speeding up because everything here we use previous chapters, like for example, steam table, ideal gas law, and so on. So this abbreviation, what's happened, simplification, or summary of what happened in the last lectures. Chapter 5, we said m dot equal rho AV. We said this volume flow rate, meter cube per kilogram. This is mass flow rate. And if it's steady, equals 0. So mass in minus our mass exit minus mass enter equal delta mass in the system, dot or without dot. This is the continuity, conservation of mass. And we see energy in minus energy out plus m sigma mass in h in plus v square over 2 plus gz inlet, call inlet, minus sigma outlet m out or exit h exit plus u exit square over 2 plus gz exit equal m2, the change in the state, u2, here is h, here is u, plus v2 v velocity, v2 square over 2 if there is potential energy or kinetic energy in a potential energy or kinetic energy in the system, minus m1 u1 plus v1 square over 2 plus gz1. So what happened here? That this means E in or exit minus E in minus E out equal delta E system, E2 minus E1. And E's are heat and work, 1, 2, 1, 2, or actually energy out minus energy in. Yeah, energy out minus energy in, correct? No, in minus out, is correct. In minus out, because this is positive inside, this is negative, which goes outside. So that's correct. Energy in minus energy out equal E2 minus E1. Energy here, heat and work, yes. This is mass energy. Unlike closed system, we don't have mass. Q minus W equal delta U because there is no mass. But here, open system, we have mass in. So we have sigma mass in, sigma mass out. Exit. The change in internal energy, all the energies minus initial. So state 2 minus state 1. This E2 minus E1. So this law, exactly this law, this equation given in the exam. The exam is open book. You don't need to memorize it. However, I recommend you to write it a lot to understand every term, every Q, every W, how to get it independently. And I give you some examples in the bottom, okay? And some definitions of everything given in the 3 pages notes. Go please ahead and open the exam. The exam given for you in the another folder is called quizzes and exams. Can you see it, guys, in the files? You will see a model of the midterm. Let's solve it in this about 30 minutes, 40 minutes. Can you see it, guys?
Yeah.
We can see it.
Yeah, open it please and follow me. The first 2 pages are summary of the equation. In the last year exam, this is the exact last year exam. The exam was closed book. That's why I provided all the equation needed in the exam and more. Every equation, rho equal m over v, mass over volume, density, even potential energy, kinetic energy, specific volume in the top. To transform from Kelvin to Celsius, from Rankine to Fahrenheit, Rankine to Kelvin, and so on. Pressure and some scales, even P vacuum, P gauge. Can you see P gauge in the middle? It's P absolute minus P atmosphere. If you have P absolute, the absolute temperature, you can get B gauge, or vice versa. If you have B gauge, you can be absolute. You have delta P if you have depth, like rho G delta H. If you have diving in the water, it means pressure build up. For example, rho G delta H, like the mercury, the manometer. Can you see that, guys? For H2O, you have critical values of temperature, pressure, volume in the middle of page 1, cheating sheet. Can you see it, guys?
Yeah, we can see it.
Okay, we have X quality in the middle of the page 1. Quality is mass of the vapor over total mass. And this is the equation of the interpolation. X unknown minus X1 over X2 minus X1 equal Y unknown minus 1. This is either similarity, the same slope, interpolation. This is the same definition of 3 words. The equation of line. Okay, guys? And 2 points on a line. Or 3 points, actually. The one is unknown and two known points. So you can get the third because you know the equation of the line. PV equal RT or Z equal PV over RT. PV equal RT, it means V ideal. Please slide to this V, it's called ideal. PV, Z equal PV over RT, this V is called V actual. Z equal V actual over V ideal. Can you see under R air 0.27 0.287 kilojoule per kilogram Kelvin? Can you see the Z equal V actual over V ideal?
Yeah.
So P reduce PR equal P over P critical. T reduce equal T over T critical. In the second half of this page, U2 minus U1 equals CV T2 minus T1. Guys, remember this equation. If you assume CV is constant, H2 minus H1 equals CP T2 minus T1. If you assume the heat capacity at constant pressure CP constant, we always have CP equals CV plus R, or K specific heat ratio equals CV over CV, CP over CV. It's called specific heat ratios. These are the information, like for example, the work done by current, by coil, isentropic, isothermal, bolotropic, the first law of thermodynamic system, definition of enthalpy. Go down in the page, definition of entropy. Everything has been given in summary for the first almost 5 chapters given here, okay? Okay, guys? Then the page is the same thing, okay? Okay, guys? Any questions? Any question, guys? Is it bad or good now?
It's good.
Guys, are you here? Can you see the
Yeah.
screen? Everything is fine?
Yeah.
Oh,
Now it's good. Now it's good, correct?
yes.
Okay. Open with me question page 3, which is question number 1. It's 18 points out of 100. 2 points each. For example, the first one, A, letter A. Thermodynamics is the science of what and what. So this were empty. So you need to write what? Energy and entropy. Is it hard or easy, guys? So these 2 points. 1 point for energy, 1 point for entropy. You have seen that in quiz of the quizzes. The first quiz, the first day, the first sentence I said in this class. Thermodynamics is the science of energy and entropy. Correct? However, I recommend to say that, but if you say something else, it's okay with me. If you said, for example, heat and work, I will consider it's correct. But I strongly suggest energy and entropy, okay? The compressibility, which is Z, is 0.95. I give you Z. What is the error in a specific volume? So I said to you hints. Look at the hint. Hint always the solution. Z means V actual over V ideal. Error be equal V ideal minus V actual over V actual times 100, correct? Look at my solution. I said error equal absolute value of V ideal over V actual minus V actual over V actual, which is 1. So it's V ideal over V actual minus 1 times 100. You see that the first line of my solution? V ideal of V actual is given. It's 1 over 0.95. 1 over 0.95. Can you see it? I can share it with you if you want. You want to share it with you?
Yeah, that'll just be better.
Sure, no worries. So here, the files. Quizzes and exams. You have midterm 1 sample, which is the last year midterm. It's fortunately the same day of your exam, July 17th. So it's a good sign for you guys. So let me share it. Okay, can you see now? Can you see it?
Yeah.
So the first one, thermodynamics, is in the science of energy and entropy. The second one, V over V ideal minus 1. V ideal over V actual minus V actual over V actual. V actual over actual is 1. V ideal over V actual is 1 over 0.95. So 1 over 0.95 minus 1 times 100. It's 5.26%. Always stick to the 2 decimal numbers. If I said in the exam 2 decimal number and you don't stick to that, you will lose a point. So do not lose points. If I said 3 decimal numbers, stick to these 3 decimal numbers. 4 decimal numbers, okay? Okay, guys? Okay. Guys, is it clear?
Yes.
Yeah.
Okay, number letter C. True or false? A specific volume. I'm describing. When you do that, you can just true or false. That's one word, but you need to think a little bit. True or false? The specific volume of saturated mixture at a given temperature is the same as specific volume at saturated vapor. So if you have water, if you have liquid water, the volume on the left the same as the right? Nope. The pressure is the same, yes. If you have the PV diagram, I'm describing to you, but in the exam you can say false and that's it. If you have this is a TV diagram, for example. Here and here, the pressure is the same. But volume here, for example, here, volume here is 0.001. Here is 1.67. So the volume here is not the same as here. Correct? Pressure is the same. So this problem, if I said the pressure of saturated mixture at a given temperature is the same as the pressure for saturated vapor at the same temperature, this is correct. But the volume is not. Correct? It means you understand, guys? You get it? This one, C. You need to understand the problem. The specific volume here, the same as here? No, this is constant pressure line. No, this is not. The same temperature. No, the pressure is the same, but the specific volume is not the same. Correct? I can close it if you want to see the screen. Here, the pressure is the same along this line. Here is specific volume, different from here. He's asking, is the volume here, specific volume, the same as here? The answer is false. But the pressure here, the same as here. Correct? At the same temperature along this horizontal line. Make sense?
Yeah.
Next one. Guys, I'm giving more much details. I'm gonna say the answer. On typical day, the outside temperature increased by 12.5 Celsius. How much this increase in Kelvin? Actually, this is 12.5 Kelvin. Delta T, this is increased by. It means delta T. So it's 12.5 K Kelvin. This is K, not R. Okay? Provide for me two decimal numbers. It means 12.50 Kelvin. Okay? Letter E, letter EI, give one extensive property like mass, volume, number of mole, internal energy, kinetic energy, anything from your choice. One intensive property, specific volume, temperature, pressure, as you wish. Letter F, is ice water, water with ice cube floating in it, pure substance? The answer is yes. Why? Because there is no chemical change. There is no chemical composition. It's pure water, H2O. Letter G, true or false? Heat and work can be associated with a process. Yes. Not a state, associated with a process, not a state. Property associated with a state. But heat and work associated with a process from state 1 to state 2. Correct? On the PV diagram, what does the area under the curve represent? It's a work. P, integration of P delta V. Is it possible to have water vapor at -10 Celsius? Check table A8. The answer is yes. If you have a very, very low pressure. Yes, it have a very low pressure. You can have a vapor of water at -10 Celsius. Vapor. If you have almost zero pressure, you can get vapor. You can just have -10 and we have vapor water. Imagine that, -10 Celsius. 0 Celsius, you can have vapor if you have a very low pressure. You can at higher temperatures, like very high pressure, you cannot have vapor. If you have, for example, pressure 100 atmosphere, it's impossible to get almost vapor. You need huge temperature. You got it, guys? So usually if you read my hints, you will see the answer. If you go table A8, you will see compressed liquid that you can have at -10. Yes, you can have a vapor. Guys, have you seen any of these questions you have never heard in the lecture? Anyone? A, B, C, D. So in the midterm, you will see a similar problem, but not the same. A similar, but not the same. Changing words, changing another problem. Okay? Okay, guys? Can go to next problem?
So for D, you were saying it's wrong, right? Because that should be Kelvin.
Yeah, this is correct, but 12.50 Kelvin, not Rankine. I'm sorry. It's my mistake.
Well, wouldn't that be 285.65?
200?
Yeah, 12.5 plus 273.
No, this is increased by, this is delta T. When you talk about delta T in Kelvin equal delta T in Celsius, because this is T minus T equal T plus 273 minus T plus 273. I'm gonna show the screen now. Look, when you subtract T minus T in Kelvin equal T Celsius minus T Celsius. These cancel each other. So delta T in Kelvin equal delta T Celsius. For example, water freezes at 273. Water boils at 373. Here, water freezes at 0. Boils at 100. The delta T is 100, correct? Delta T is what? 100. Delta T is what? 100. So delta T Celsius equal delta T Kelvin, correct? Correct?
Yes.
Make sense? So delta T in Celsius is equal increased by. Read the question carefully, guys. Some words are tricky. Air temperature increased by. It means delta T is not temperature. It was like, for example, 100 became 112.5. So increased by 12.5. Okay? So I want to make sure that you're reading the problem carefully. So the increased to is something else, but increased by, it means delta T. Okay, and actually when I said the question, I said, how much is this change? This is a change in Kelvin. So I asked for a change. So if you do not notice increase by, you need to see this change underline. You have underline under the change. You see the word change? I have underline to show to you, emphasize that this is change. Okay, make sense? Problem 2, as you can see, is so simple problem. I will draw it first, then we'll discuss. Read it. It's a kind of piston in a cylinder. It has 3 chambers. 1, 2, 3 chambers, 3 rooms. Oops. Something like this. We have 1, 2, 3. 1, 2, 3. Hey guys, I'm gonna stop sharing. 1 second, okay? So this is a problem. Problem number 2. Something so simple like this. I said this is a 3 chamber. Number 1, 2, 3. Pressure always normal on the wall. Always normal on the wall. So pressure 1, of course, upward. This is called imbalance. It means net force is 0. So F1 equal F2 plus F3. This is upward, these are downwards. F1 is P1 area 1. Area 1 is this diameter. Equal P2 area 2, which is this annulus area. This area is annulus. Pi r square minus pi r square. F3 is this area, which is P3 A3. Can you imagine that, guys? So area 2 is this area. It's annulus area. The pressure applied on this area. This is called annulus area. A circle with a hole inside. Can you imagine that, guys? Okay, I will share again the problem. So this problem like this is a cylinders piston diameter ratio. I give you D1 over D2 equal 3. Diameter 1, the big diameter, divided by diameter 2, which is the small diameter, ratio is 3. I give you pressure in the chamber 2 is 3 atmosphere, the middle room here, 3 atmosphere. Chamber 3, the small room, is 2 atmosphere. What is the pressure in 1? So the force balance, F1 minus F2 minus F3 equals 0. I give it in a hint. This piston does not move. It means 0 net force. F1 minus F2 minus F3 equals 0. Can you see that? The hint? Hey guys, can you see the hint?
Yes.
So it means P1A1 minus P2A2 minus P3A3 equals 0. So pressure times area. The area 1 is pi d1 square over 4. P2 is an annulus, pi over 4 d1 square minus d square, d2 square, because it's an annulus. Diameter the bigger, square minus diameter smaller. The big area minus small area give you the shed area in the board. Minus P3 area 3. Area 3 small area, pi over 4 d2 square. Unfortunately, you don't have here d1 or d2. You have a ratio. So we can divide the whole thing by d2 square. Can you see? I divide by pi over 4 d2 square. It became simply P1 times d1 over d2 square minus P2 times d1 over 2d square minus 1 minus P3. You have d1 over d2, yes, which is 9. Ratio is 3, square is 9. You have P2, which is, I think P2 was 3 atmosphere. P3, which is, I think, was 2 atmosphere. So you can substitute by all of them. You can get what? The P1, which is finally 2.88 atmosphere. He said, give it me in PSI. Give me the value in PSI. What the pressure in chamber 1 in PSI. If you go back to the first page, go to the first page. Are you following me, guys? Here, 1 atmosphere equal 14.6 PSI. Correct? This is the ratio. If you want, you can remove 1 atmosphere by replacing by 14.7 PSI. 14.696. So you can go down, replace the word atmosphere, this word, remove this word, and put 14.7 PSI. It means 42 PSI. Is it hard, guys? Is this problem a little bit hard? So imagine I give you, for example, P, this force, and you just write the first line. If this problem 18 points, you get 4 points. If you write PA minus PA minus PA equals 0, P11, P1, P2A2, P3, you just get 4 points. If you expand it, you get another 4 points. If you substitute, you get another 4 points. If you get the correct answer, you get another 4 points. You get the 18 points. So whatever you write correct, you're gonna get 0.4. Even something so simple, but you get some points for that. Okay? Okay, guys? Are you following me? Problem 3. Problem 3. A frictionless piston cylinder. There is no heat. Frictionless means there is no heat loss during movement of the piston in the cylinder. Initially contains volume. I give you the volume. Liquid, saturated liquid. It means X equals 0. Saturated liquid water. This is a long saturated liquid line. X equal 0. So if you look down in my PV diagram, I put 0.1 here in saturated liquid line. Can you see it? Because he said saturated liquid water. X equals 0. And you have the total volume, 0.02 meter cube, about 20 liter. The piston is free to move. Pressure is constant. Free to move, pressure is constant, 800 kilopascal. Free to move, pressure is constant, outside and inside. So this process, if you plot in the PV diagram, it's a constant pressure line, horizontal line. In the TV diagram, it's a little bit different, but it's still constant pressure line. The constant pressure line in TV diagram, you remember the Brook line? Okay? Okay, guys? So pressure is 800 kilopascal. So you have X1, you have P1, and actually you have P2, P2. The water heated to raises 2 means the temperature, not by, this is 250. It means the temperature at state 2 is 250. So now I have a state 1 completely, X1 and P1. I have a state 2, P2 and T2. First, the first require plot. Draw for me, plot, read carefully, plot the PV diagram of this process. Showing the states 1 and 2. So if you plot PV diagram, this is horizontal curve from 1 to 2. Maybe 2 inside, maybe outside. We don't know yet. So 1, of course, saturated liquid. He gave it to us. 2, we don't know yet. You can keep it, but you are sure it's a horizontal line, either to the left or to the right. But I'm heating up because temperature increases, raises 2. Yalla, find the work. Work at a constant pressure process. Simply, you see the equation next to it, PdV. The heat, it's Q equals delta H, because here we do not have, the pressure is constant. This is piston cylinder, free to move. Q equals delta H. Q equal delta, or Q minus W equals delta U. Yes, it's both correct. Both are correct. You have the W and you have delta U, you can get Q. Okay, guys? State 1. You have X1 and P1. You can get V1, H1, U1, anything at state 1 from table A5 because pressure is input. Make sense? State 2. You have P2 and T2. If you go to table A5, you will not find this state. So it means your temperature is greater. It means you have superheated. To go to table A6, you get V2, H2, V2 at 800 kilopascal, which is 0.8 megapascal, and temperature 250 Celsius. The mass is volume per unit is physical volume. It means you can get the mass, divide the volume, 0.02 meter cube, over the specific volume, V1. You can get the initial mass, which is the same for all the process, because this is closed system problem. The mass 1 equal mass 2. But volume 1 not equal volume 2. A specific volume 1 not equal specific volume 2. But mass 1 equal mass 2. Make sense? This is closed system. Control mass. Mass is constant. In the very edge of this page, W equal PdV. M times pressure times V2, specific volume 2, minus V1. Everything I have for pressure, 800 kilopascal. Why I use this equation, guys? Why W equal PdV? Why W equal PdV, guys? Can somebody tell me why W equal PdV? Because the piston is free to move, constant pressure. When I say free to move, it's constant pressure. So when I said, for example, W is integration PdV, correct? P is constant. It means P delta V. It means P V2 minus V1, or M P V2 minus V1, correct? Correct, guys?
Yeah.
So you're supposed to say to me, this is isobaric process. The pressure was constant. The piston is free to move. Free to move means what? If you have problem like this, and this piston free to move, pressure here is equal to here. Anything free to move, if I'm heating up something, the pressure is supposed to build up. But this is free to move. It means it will move to keep this piston always has the same pressure. So pressure will not build up. Of course, you will not have here 1000 and here 200. It's impossible unless you hold it. You apply force. But because it's free to move, it's 200, 200, 800, 800, 500, 500. The pressure across the piston is constant. It's free to move. Make sense? So you need to understand what I said. I have said it many times. Free to move means constant pressure process. So pressure can be get out of the integration. This is simple integration. PdV, get P outside. Integration delta V is V2 minus V1, which is mass times pressure, specific volume 2 minus specific volume 1. Okay? Okay, guys?
So whenever it's a piston, the mass will always be constant.
Of course. Constant control closed system is called control mass problem. Controlled mass is the same. I do not add mass. Where from mass come from? From where?
Okay, thanks.
Did I add mass? No. Did I remove mass? No. It's not open tank. It's not has a hole or fan or compressor. It's closed system, confined mass. Okay. Now, letter B, Q equals delta H or Q minus W equals delta U, as you wish. I did both. The first one, Q equals delta H. So just mass H2 minus H1. Say you got H2 minus H1. Or you have W already. Get delta U, mass U2 minus U1. You will find the same answer from the first approach or second approach. You got 39.99 megajoule or 39.99 megajoule from either first approach or second approach. Of course, you get the same answer. So don't worry. If you use this approach, you get the same answer as the second approach. Okay? Okay?
Sounds good.
Okay, this problem is so important. Problem number 4. This is one of the problem in the homework 1, I guess. Homework 2. A student living in a 3x5x4 room turns a 130-watt fan. This is a very, very fundamental problem in thermodynamics. Before she leaves the room on summer day, like today, she turned the fan on. It has room by 3x5x4 room size. You have the volume, you mean? And she keep everything closed. The window, the doors, everything is tight. Everything are tight closed. This is called closed system. There is nothing escape, heat or energy or work. Any heat or what? Our windows are neglected. She said everything is disregarding. I neglect all the heat transfer through the walls or the windows. Okay? Before the last line, determine the temperature in the room when she comes after 7 hours. Comment on your results. So give me the temperature after 7 hours. Comment on your results. Okay. We have a specific heat. Guys, the first equation, can you see Q equals delta U? Q equals delta U. Can you see it? The first equation.
Yeah, we can see it.
Yeah, this equation was Q minus W equals delta U. This is closed system and does not have any work. So W is 0. Just Q equals delta U. The heat I added to the system equals delta U. Okay? Delta U is MC delta T. C is CV or CP. The heat capacity, actually here is CV because it's delta U, not delta H. So for some, we have said this many times, but we're gonna say it again. We have just a few minutes, we're gonna finish. Guys, we have C for gases. We have CV and CP. CV for U, CP for H, correct? For liquids and solids, we have just one C, just one C. So for example, Q or U, I'm sorry, U equals CV delta T. Delta U equals CV delta T. If the CV is constant, if the CV is constant, if the CV is constant. Here, delta U, just C delta T. For example, water. For example, solid. So for example, if I want to heat up water, the heat needed, there is no work. Heat needed, it's delta U. It's MC delta T. This is a very fundamental equation for liquid and solid. Just this, because we have one C. For gases, it depends. CV and CP. CV, delta U, CV delta T. Delta H is CP delta T. If we assume the heat capacities are constants. So go back to work, back to the problem. We have Q equals delta U. It was Q minus W equals delta U. This is a closed system, constant volume. The volume does not change. The work is 0. So Q equals delta U. Delta U equal M delta U small. Delta is specific internal energy. It means the last part of the equation 1, mCV T2 minus T1. CV from table A2A. T2, we don't have it yet. T1, we have it. Or we need to see how much temperature increased, which is delta T. Okay, guys? Do you have T1 or not? You don't have T1,
Yeah.
but we can get delta T. We have delta T, we have T1? Yeah, we have T1, which is 20 Celsius. Okay? Okay, guys? Second equation. The heat added to the system is Q dot time delta time. I said to you, I give you 130 watt fan. It means every hour or every second, I use 130 watt joule. What is 130 joule per second? If I multiply this by how many seconds, I get how many joules? 130 watt times 7 hours, 3,600 seconds in each hour. It's 3.276 megajoule. Megajoule. The end of equation 2. Can you see the end of equation 2? Q dot times time equal you how many joules have you used in this fan for 7 hours. Can you see it, guys?
Yep.
So mass can be obtained from First law, ideal gas law, PV equal MRT. PV equal MRT. You can obtain the mass. You have pressure of the room. You have the volume of the volume, which is 3.5/4. You have the R, air. You have temperature. Assume the temperature initially was constant. Then get the mass, which is constant. If you even get hotter, it's the same mass. This is closed system. You have T1, 20. You have how many joules? 3.276 10 to the 6 joule. The unknown is T2. And of course, gas constant from table A1 287 joule per kilogram Kelvin. You can get the mass, you can get the T2, which is 83. Wow. Initially, it was 20 Celsius. Finally, it became 83. Remember, guys, always substitute by Kelvin, absolute temperature. I know that the lecture is over. If you want to leave, you can leave. I'm just giving the rest of the exam. If you want to leave anytime, you can leave, guys. No problem. T2, it was in Kelvin. Always substitute by Kelvin. Do not use any Celsius unless you have delta T, but it's okay. Stick to Kelvin, then transfer to the Celsius. So temperature was 20, became 83. Was 20, became 83. So what happened? She added more than 63 degrees to the system. Why? When she turned the fan on and the door is closed and the fan is closed, energy keep adding to the system, which is closed. The energy temperature increases, became 83. It was like 30, became 83. So if you are having a room with a fan, turn it on, and everything is closed, isolated, the temperature will increase. The temperature will increase. Make sense? This is the comment I want to hear from you. Adding energy or heat to a closed system increases internal energy. Temperature will increase. So the temperature for a room increased. So this girl, she was correct or not in this action to turn the fan on. She think the heat, the temperature will be cool when she come back. She was wrong or correct? She was wrong or correct, guys?
Correct.
She was wrong. She turned the fan to cool down. Before she leaves the room in the summer, hoping that the room will be cooler when she comes back. She is wrong in her expectation. If you turn energy source in a room and you leave it closed, even if it's a fan, temperature will increase, not decrease. Okay? Okay, guys? Read the second line and third line. She turned the fan on before she leaves the room on the summer day, be hoping that the room will be cooler when she comes back in the evening. Does it make sense? No, that's wrong. Correct?
Yes.
So determine that problem number 5, 22 points. Determine the enthalpy, delta H, change, delta H, of nitrogen. Nitrogen means, right above it, it's ideal gas. In kilojoule per kilogram, as heated from 400, this problem we have solved it in the lecture, from 400 T1 to 200, 800 T2, using table A2TC with empirical specific heat. Remember, specific heat in the table was per kilomole, but we wanted per kilogram. All you need to do, So simple. It's what? Divide by molecular weight. It will go from per kilomole became per kilogram. Divide by molecular weight. Cp at constant average temperature. Every Cp at the average temperature. Cp at room temperature. Table A2A. Comment on the errors. Of course, we can get the error. What do you think in these errors? If we have from 300 to 350, of course, if the temperature is smaller and closer to room temperature, the error will decrease. Just comment. Do not calculate. The last point. What do you think of these errors if the change in temperature are from 300 to 350? Do not calculate any new values. Just comment. They will be larger or smaller? Of course, smaller. Why? Because we are closer to room temperature. The smaller you are to room temperature, the smaller the error is between calculation from A to B to C. C is the worst, but it can be very good if you are nearby room temperature, like the comment. So A is the best because it's empirical. B, average, little bit error. C is the worst. However, C would be good if you are nearby. This problem we have solved in the lecture. I'm not going to solve it again. Okay. Last one was from another chapter, which is chapter 5. We do not have it. I'm going to ask for, if you have the equation, just ask about it. But for now, you have seen this problem, guys. I can ask you anything in the problem related to these problems. Please make sure you can solve such a problem yourself. All the problems in lectures, all the problems in work, quizzes are important. Again, I'm saying it again over and over. All the problems in the lectures, make sure you solve them yourself by your hand. Make all the mistakes yourself now. All the quizzes problems, all the homeworks problems. These 3 pieces will be the final midterm and the finals, but with different numbers, a little bit mixed thoughts from here and there. Okay, guys? Any questions?